page 6 of functions. State which of the following are linear functions. Now there's a couple ways to do this, and you know, I'm going to show you a way to do it without the calculator, but then we're going to use the calculator because we always have access to the calculator. First of all, remember that you know, vertical lines look like this. You know, y equals a number. I'm sorry, horizontal lines. Vertical lines look like this. X equals a number. And then, of course, there's the diagonal lines. And the diagonal lines kind of look like this. You know, we have the gradient intercept or slope intercept form. We have the point gradient form, and we have the standard form. Something like that. And if you look at each one, you can kind of see that there's like a pattern here where basically the x's and the y's, you know, they're not squared or anything. They're always in the numerator. And, you know, at most there's like a number multiplied to them. And then you can always also have like these extra numbers that are just by themselves, those constants. You know, you can have those. Those are no problem. Still linear. All right. So using that method of identification, it looks like this might be linear, this might be linear, and this might be linear. This is looks like a horizontal line, but this is not because the x is in the denominator, right? Just to verify that, let's graph some of these. Okay. So I'm not going to graph the horizontal line. That's kind of boring. But I can graph like this one. This one is a little bit weird, right? Y equals 5 times x minus 2. Somebody might get confused by that because it's not really any one of these regular forms. So I'm going to graph that one. And then I'll also graph 2 over x plus 1 just so that you see what that looks like. 2 over x. Oops. I don't want to put it all in the same function. I want to put them separately. Oh, I didn't want to do that either. Okay. Sometimes when you want to do delete, you do clear, and vice versa. Okay. 5 times x minus 2 in parentheses, and then I'm going to put 2 divided by x. If you want to be really safe, you should put 2 divided by x in parentheses if you're not good at PEMDAS. I know it's fine because I'm a math teacher. Okay, graph. And remember, one of them is blue and one of them is red. The blue function looks like a line, and the red function does not. So the blue function is linear, so we were right. 5 times x minus 2 is linear, and 2 over x plus 1 plus 3 is not linear. Okay? All right, moving on. Number 2, for each context A through D below, identify the independent and dependent variables and their units where appropriate. So remember in the investigation where we learned that independent variable is associated with x and dependent variable is associated with y. Okay, and their units. Okay, so let's take a look at that in a minute. Determine whether a linear function can be used to model the relationship between the two variables, and if so, state the rate of change. Okay. And finally, parking at an airport is charged at... Okay, so now what we're going to do is we're going to do these two things for each case. Okay, so case A. Parking at an airport is charged at $18 for the first hour parked and $12.50 for each subsequent hour. Okay, so one of the ways you could figure out if this is linear is you could write a model for it. And the other is you could like write out some data points for it. So we'll do the data points first because I think it's easier. Okay, so what I'm going to do is I'm going to have the first variable, the x variable, the independent variable is going to be, let's see. So it's the parking charge is the output, and the input is the time, the number of hours. So I'll put time as the independent variable, and I'll put cost as the or the charge as the dependent variable, and their units are going to be dollars for the cost, and it's going to be hours for time, right? And let's put some sample points here. For example, first hour parked is $18. Okay, so first hour is $18. And the second hour is $12.50 plus the $18 for the first hour, right? So for 2 hours of parking, you would need to do 18 plus $12.50, which would be $30.50. And for 3 hours parked, it would be $12.50 plus $30.50, so that would be $42.50 plus 50 more cents, $43. So $43 for 3 hours parked. 4 hours parked, we would add $12.50 again, so it would be $55.50. I'm adding these in my head, and I hope I'm not making any mistakes. Okay. So we have a few points here, and we want to know if this is going to be a linear function or not. The way you can figure out this is a linear function is the same way we can check to see if something is an arithmetic sequence, because linear functions are totally related to arithmetic sequences. Okay, the difference between an arithmetic sequence and a linear function is arithmetic sequences are discrete. We don't define the points in between the whole number values of the x. Remember the n values, they're always whole numbers, right? And a linear function, they are defined in between. But sometimes if we write it out like this, you can't really tell the difference between a linear function and an arithmetic sequence because they advance the exact same way. The x values just go 1, 2, 3, 4. The y values will go up by the same amount every time. If you remember, every time we went from one number to another here, we added $12.50. So this is like arithmetic sequence where the d value is $12.50. Okay, so yes, this is linear because, you know, it's an arithmetic sequence in nature, and the difference between each two y values is $12.50, so it's always the same amount, and so that would be the rate of change. The rate of change is $12.50. Okay, all right. Oh, and the other way to do it, okay, is you could go into the calculator, and then you could go to Stat, and you go to Edit, and, you know, I think that this method is maybe good for someone who really loves the calculator, okay? And if you're really good and fast at using it, you could do this. Okay, so... okay, I typed in all the numbers that I just, oops, it should be 55.5, right? Okay, I just typed in my 4 ordered pairs, and then I'm going to graph these ordered pairs. First, I need to get rid of my y equals, the things that I put in my y equals during the last problem. And then I'm going to graph them. But to graph them, I need to go to second stat plot. And this is why I said you really have to love the calculator, because I'm going to teach you one extra thing on the calculator. You want to turn plot 1 so that you are going to do a scatter, and you're going to press on. So do you see how type is like on the first thing? That's a scatter plot. And our list, it's L1 and L2, and we're going to use this little square for our marker. And enter, or we're just going to just do second quit to get out of that. And then we're going to graph it. I think we're going to have to do zoom though, because probably it's going to go off the screen. Yeah, so like the first point, 1,18, isn't even on the screen. So let's do a zoom. And for this zoom, we're going to use zoom stat, because zoom stat is going to zoom it so that it fits our points. And by looking at the points, you can see it's a line, right? So that's one way you can figure out what the if it's linear or not by graphing it like this, okay? Now in this particular problem, they ask us to find the rate of change, right? The rate of change, which is the difference between each subsequent y value. So you really are kind of stuck. You really have to analyze it from that direction also. So it doesn't really help you in this case to do stat plot. Okay, the population of a fish in a lake declines by 7% each year. Okay, so, you know, somebody might be confused by this because let's say that you're going to make a table for this one. You don't know what numbers to put because it never says what the first number would be. Okay, but let's put fish, which would be the output or the dependent variable, and let's put year or time. Okay, and so the unit used for time is year, and the unit for fish is just fish. Okay, and so we'll do like year 1 and year 2 and year 3. Okay, but they never tell us what year 1 is. They never tell us what the population of fish is, and we're going to find this out in a future unit. But if they ever give you a case where they don't tell you the initial amount, and you're supposed to kind of figure it out somehow, often what you can do is you can invent your own amount, okay? And I would say that 100 is a very convenient number to use because it's very related to percentage. So let's say that the first year, the number of fish is 100. And then it says that every year the fish in the lake decline by 7%. What is 7% of 100? Oh, I'm so glad we chose 100 because 7% of 100 is 7. We didn't even need to use a calculator. So it says it declines by 7% each year. So the first year it's going to decline by 7 to 93, right? And then the next year, is it going to decline 7 again? Well, not anymore, because if it declines 7%, what we need to do is we need to find out what 7% of 93 is, right? So we're going to take 93, we're going to multiply it by 0.07, which is 7%, and we get 6.51. So now we're going to subtract 6.51, and then we're going to end up with something like 93 minus 6.51. It's going to be 86.5. Okay? So in this particular case, is this linear? No, because first we subtracted 7, then we subtracted 6.51. Obviously not linear. Okay? What about case C? It charges a value-added tax, VAT, of 22% on all purchases. The amount of tax you pay depends on the amount of your purchase. Okay, so for example, if you, let's say the amount of your purchase and the amount of VAT. So we'll have P for our independent variable, and that will be in euros. It's the amount of the purchase. And the VAT is also euros, okay? And so let's say we pay 1 euro. What would be the amount of VAT you would pay? It would be 1 times 0.22, so it would be 0.22. 22 euro cents or whatever. What if you spent $2? $2 or 2 euros. 2 euros times 0.22 is 0.44. And 3 would be 0.66 and so on, okay? And if you look at this, you can see that for each euro purchase, you are going to have 0.22 additional euros to pay. So it looks like this is an arithmetic sequence, which means this is a linear function. Okay, and the rate of change is 0.22 each time. Okay? All right, let's go to D. Sal's ski resort notices the falling trend in sales of daily passes. So if the high temperature is very cold, then there are more passes sold, right? Because if the temperature is 7 Celsius, which is slightly warmer, then only 300 passes. If it's negative 4 Celsius, much colder, it's going to be 430 passes. Okay? All right, so let's take a look at this. What's the independent variable? So the independent variable is the daily high temperature, and then let's call that capital T. And then the y variable, or the dependent variable, is the number of daily passes sold. Let's call that P. And we want to see if this is a linear function or not. And this one's pretty tough because if you look at the x variables and the y variables, like especially the x variables, if you look at the x variables, they're not going up, 1, 2, 3, 4, right? They're like separated by irregular amounts. So it's kind of hard to judge whether the steps between the p-values is regular or not. So this is kind of like an optimum case to do using stat edit. So why don't we do it with stat edit, okay? So for L1 and L2, I'm going to put in the capital T and P values. So L1, I'm going to put -4, -1, 3, and 7. -4, -1, 3, oops, whoa, what did I do? Stat, edit, -4, -1, oops, no, darn it. Okay, -4, go down, -1, 1, go down, 3, go down, 7. I'm doing all the temperature values first. Go down. Okay, and then for the dependent variable, I'm going to put 430 and 406 and 374 and 342. And I'm going to graph it. Except it's going to be off the screen, so I need to, did it adjust automatically? So I need to first of all adjust my x values so that it goes from -4 to 7. So I'm going to change the window, and I'm going to put -4 and 7 for my x min and my x max. And for the y min and y max, I could either, I think I'll put 0 and 430. Of course, you could use stat plot, remember? And they look linear, so I think they are linear, okay? And it says to find the rate of change. So guess what the easiest way to find the rate of change of these is? Yes, our old friend, stat calc ln reg, because the rate of change is actually the slope. So if we just do stat calc ln reg on it, it's going to give us the rate of change. The rate of change is -8, okay? I think that's all we need to do, right? We just need to figure out if it's linear. Yes, it's linear. We saw visually that it was linear. And we also can see that the slope is -8, and that is the change, okay? You can actually do that on any of these problems. You can just type it in stat edit, and then you could do stat calc ln reg, and the a value, or the slope, is going to be the rate of change. Okay, all right. Number 4, the table shows values for a function y equals f of x. Determine whether or not the function defined in the table is linear. In this particular case, this one's more well behaved than the last one, because look, the function, the x values jump from 1, 3, 5, 7. They always jump by 2s. So since it jumps by 2s, we could just look at the jumping sizes here and to see if they're also the same. And if they're both the same, then we're going to know that it is linear. Now, like the first one, we jump by 4. And the next one, we jump by 4. And the next one, we jump by 5. So, no, this is not an arithmetic sequence, not linear, okay? All right. Another way you could check to see if it's linear is you could put it into stat edit and plot them. And you'll see that the last point was like a little bit out of line. It should be like 14 instead of 15 for the thing to be perfectly linear, okay? Next one. The table shows some values for a linear function f of x equals mx plus c. Doesn't that look familiar? Mx plus c. Mx plus c is the slope-intercept or gradient-intercept form. And then they give us several points. It says write down the value of b. Okay, so there's a couple ways you could do this. One of the ways you could do this is you could check the jumps here. So like the jumps here are very well behaved, plus 2, plus 2, plus 2, plus 2. If the jumps in the x value is well behaved, that means the y value should also be well behaved. So like, do you see the first from 5 to 6.5, it jumps by 1.5, right? So jumping from 6.5 to the next one, it should also jump by 1.5. So the b value should be 6.5 plus 1.5, which is 8. Okay, and then if I could test it again, if I add 8 plus 1.5, I get 9.5. So it looks like that works. Okay, and it also asked us to find the value of the slope. The value of the slope, we could use 2 of these points, right? We could take these 2 points, and then we could use the 2 points to find out what the slope is just by doing stat edit, right? So let's do that. We're gonna we'll go to stat, edit, and then we're going to put 1, 5 and 3, 6.5. So let's get rid of the data that's here. So we're going to put 1, 5 across the top, okay? And then I'm going to put 5, 6.5 in the second row. I'm sorry, 3, 6.5. Okay, and then stat calculin reg. And then, yes, L1, L2. And the slope is 0.75. And then it asks for f of 0. Remember, f of 0 is the y-intercept because it's the y value when x equals 0. Okay. By the way, let me show you how to, like, let's say that you get a line and you want to graph it immediately, and you don't want to like type it in afterwards. There's an extra thing that I don't remember if we've ever used before, but if you go into stat calculin reg, you could actually tell it, hey, I want you to put this in y1, okay? The way you do that is you go to where it says store reg equation, and then you say vars y bar function y1. Saying I want to put it into y1. So it's going to put my function, which was 0.75x something, it's going to put this in y1. So if I press on y1, look, it's there. There it is. So now that I have it there, if I want to find the y-intercept, guess how I do that? I can do that by doing graph trace 0, right? Remember graph trace 0? Trace. Okay, this looks really weird because and the zoom is like fit to the last problem. So let's adjust the zoom. We'll do zoom standard. Okay. And look, we're going to see how well the line goes through these 2 points. Perfectly, of course. Okay, then we're going to do trace 0 to see what the y-intercept is. Trace 0. Oops. That didn't work. Try again. Trace 0. Okay, it's freaking out. I think it's because of the plot stuff. So let's turn off the stat plot. Second stat plot. I'm going to turn this off. Okay, now let's graph, and it's not going to graph those 2 points. And then I'll do trace 0. Trace 0. Yeah, now it's acting normal. Okay, and the y-intercept is 4.25. What a surprise! Actually, not a surprise at all, because you remember, when you did stat calculin reg, the b value is 4.25. Okay? I think that's it for this page.